In this video, we are going to look at another method of proof called proof by contradiction. Before we get into the mechanics of proof by contradiction, we're first going to look at an example where we use what's called accommodation in reasoning. We're going to show how this gives us a new way of proving statements, namely proof by contradiction. We're going to formally describe what proof by contradiction is, and then we're going to prove a theorem using proof by contradiction. So before we get started with the proof part, I'm going to tell you about a conversation I actually had with one of my kids. So my son's name is Eli, and he told me one day, on a Saturday, I'm going to play with Xavier at school tomorrow. And I said, hey, but Eli, tomorrow is Sunday, and you don't have school until Monday. How will you play with Xavier at school? At this point of the conversation, Eli understood that he was not going to play with Xavier at school the next day. And the interesting thing about this is I didn't actually have to tell him that. It was just after those two snippets of conversation. And Eli was using what is called in psychology accommodation. And what that means is you receive some information that contradicts your current beliefs. And what you do is you change your beliefs to be consistent with that new information. And this kind of reasoning is fundamental in the method of proof by contradiction. So let's see if we can repackage this conversation I have with Eli into an actual theorem. It's not going to be a super mathy theorem. It's going to be a theorem about Eli. So here's the theorem. Eli will not play with Xavier at school tomorrow. And here's what the format of the proof is going to be according to how this conversation actually happened. The first part is, well, Eli claimed, and he did, he claimed that he will play with Xavier at school tomorrow. That's how the proof started. Then I mentioned the fact that tomorrow is Sunday, so neither he nor Xavier will be at school, so it's impossible for them to play at school tomorrow. Eli recognizes that this contradicts his claim that he will play with Xavier at school tomorrow. And then we can immediately conclude that Eli will not play with Xavier at school tomorrow, and that actually completed the proof. Again, I didn't have to say anything after that. Eli and I both understood that he would not be playing with Xavier. So as you can see, as the syntax of this proof, the format of this proof is very odd. It's very unusual. But the logic is airtight. So here's how proof by contradiction is going to look like in general. First of all, proof by contradiction is not limited to certain types of statements like contrapositive was. That was limited purely to conditional statements. This can be used on literally any statement that we want to prove. So suppose that we are trying to prove any statement, we'll call it P. Here's what a proof by contradiction looks like for that statement P. The first thing we're going to do is assume that our statement P is false. And another way of saying that, a more useful way of saying that, is we are going to assume that the negation of P is true. Right? And this is exactly what happened when Eli assumed that he would play with Xavier, even though our theorem said he would not play with Xavier. And then starting with the assumption that the negation of P is true, we're going to follow this assumption logically, just like any other proof, and hopefully end up with a statement that we prove that is clearly false. In the proof that I gave you in the previous slide, that's like when Eli showed that he would be playing with Xavier at school on Sunday, which is impossible. It cannot possibly be true. Once we get to that statement that is clearly false, which is, by the way, is called a contradiction, we declare our theorem to be true, and then that makes the proof complete. The proof is finished at that point. So one of the things that is going to be mechanically important, as you can see, the very first step is we have to find the negation of our theorem. So finding negations of statement is going to be extremely important in proof by contradiction, which, let's be honest, it was really important in proof by contrapositive too. There we had to find the negation of two statements, the if part and the then part. So as you can see with these new proof methods, finding negations of statement is going to be very important. All right, so here's another entertaining way of thinking of proof by contradiction, if it helps, because I like to think of it because we get to play a prank on Peeves, and Peeves is always a pain in the butt, so he totally deserves it. So first of all, we say our theorem is true. Peeves says that we're wrong, our theorem is actually false. And then we say something like, fine, Peeves, my theorem is false. Then you follow this assumption logically to a clearly false conclusion, which Peeves has to go along with. With all Peeves' faults, he is bound by logic. If you logically go to a clearly false conclusion, Peeves has to follow you there. And then Peeves gets mad and storms away, and you just say, hey, my theorem is true. So here's a theorem that we're going to prove by contradiction. Let a and b be integers. If a is even and b is odd, then a squared plus 2b squared is not divisible by 4. Now the first thing I want to note, just as we did in the proofs that we did by contrapositive, if we try to do a direct proof, this would be difficult. The assumptions are fine. We assume a is even, we assume b is odd. But we want to show that a squared plus 2b squared is not divisible by 4. Proving something is divisible by 4 is relatively straightforward. We have a nice definition of what it means to be divisible by 4. But there are lots of ways that a number can be not divisible by 4. And so that makes it extremely chaotic to try to prove directly that a squared plus 2b squared is not divisible by 4. So what we're going to do, and this will happen anytime you're trying to prove a not statement. Anything that says not. Not always. There are some cases where the not statements aren't too bad, but in almost all cases, proving a not statement is very difficult to do directly. All right, so we're going to try proof by contradiction. So the first thing we're going to do is we're going to assume our theorem is false. And that is actually pretty tricky because our theorem is a conditional statement. It's an if-then statement. So what does it mean for an if-then statement to be false? Well, remember, our if-then statement is false precisely when the if part is true and the then part is false. So the negation of an if-then statement is actually an and statement. So we assume that the if part is true. In other words, we assume that a is even, b is odd. And we assume the then part is false. The then part is a squared plus 2b squared is not divisible by 4. So when we negate that, we're assuming that a squared plus 2b squared is divisible by 4. So we're actually assuming three things. A is even, b is odd, a squared plus 2b squared is divisible by 4. And yes, and another way of saying is divisible by 4 is that 4 divides evenly into a squared plus 2b squared. And then we're going to show, well, we don't exactly know what we're going to show. All we know is whatever it is that we show, it has to be a false statement, has to be clearly false. All right, so let's get started. We're assuming that 4 divides a squared plus 2b squared. By definition, that says a squared plus 2b squared is equal to 4k, where k is some integer. Now, a is even, b is odd, and if we want to, and that means that a is equal to 2 times an integer, b is equal to 2 times an integer plus 1. Those two integers are m and n. We want to give them different names than the k because they might all be different. So let's take a look at a squared plus 2b squared. Well, on the one hand, a couple lines up, we show that that was equal to 4k. But if we substitute 2m in for a and 2n plus 1 in for b, we get 2m quantity squared plus 2 times the quantity 2n plus 1 squared. Then we can square out the 2m squared and the 2n plus 1 squared. We can do some more simplifications, and what we end up with is 4m squared plus 8n squared plus 8n plus 2. So the two computations we did, we got two expressions for a squared plus 2b squared. One was 4k, that is what, 3 lines up? A squared plus 2b squared equals 4k. And then just at the bottom here, a squared plus 2b squared is equal to 4m squared plus 8n squared plus 8n plus 2. Since those are both equal to a squared plus 2b squared, they must be equal to each other. So 4m squared plus 8n squared plus 8n plus 2 is equal to 4k. All right, so now we've derived ourselves an equation. Let's see if we can play with it. Well, we're going to do some algebra to it, and some of it may not seem very intuitive, but it turns out it's going to be really useful if we move everything from the left side to the right side except that 2. So if we do that, we get 2 equals 4k minus 4m squared minus 8n squared minus 8n. And the reason that turns out to be useful is if you look at that right-hand side of the equation, all of those terms have a common factor of 4 in them, which means that we can factor out a 4 from each of those terms. So we get 2 equals 4 times the quantity k minus m squared minus 2n squared minus 2n. And now we can divide both sides by 4, and we get 1/2 on the left. We get k minus m squared minus 2n squared minus 2n on the right. And you might notice something funny about that. On the left, that 1/2, that is definitely not an integer. But on the right hand, the k, the m, the n, and all the squaring and multiplying and subtracting tell us that that is going to be an integer. So on the left side, we have not an integer. On the right-hand side, we have an integer. And yet somehow those two things are going to be equal. Is it possible for a not integer to equal an integer? No, it's a contradiction. That's a clearly false statement. So there's our contradiction. There's the end of our proof by contradiction. All right, so we outlined it. Now let's see if we can write it up in a formal proof. As with any unusual proof method that we use, that includes the contrapositive that we did before, it includes any time we use a logical equivalence, we have to warn our reader that what proof method we're actually using. So the first thing we're going to say is, hey, we're proving this by contradiction. And then, since our reader is primed to understand contradiction, that means the next thing we're going to do is assume that our theorem is false. So we're going to assume a is even, that b is odd, and that 4 divides evenly into a squared plus 2b squared. Right? And then we're going to use this to prove a contradiction. So we're telling our reader, what are we assuming and what are we going to show? And when we say prove a contradiction, we don't have to tell them what the contradiction is. They already know this is a proof by contradiction, and at some point we're going to prove something that's clearly false. We're just letting them know that that's what we're doing. So now we're going to use our definitions. We know a is even, so we have a equals 2m for some integer m. We know b is odd, so we have b equals 2n plus 1 for some integer n. We know that 4 divides, and then that gives us, if we put those two things together, that's where we're going to take the a squared plus 2b squared and substitute a equals 2m, b equals 2n plus 1. We're going to do all that algebra to end up with 4m squared plus 8n squared plus 8n plus 2. Now we're going to use our other assumption that 4 divides evenly into a squared plus 2b squared to write a squared plus 2b squared equals 4k for some integer k. And now we're going to put those two pieces of information together. When we put this together with a squared plus 2b squared equals 4m squared plus 8n squared plus 8n plus 2, we get, well, that those two things are equal. The 4m squared plus 8n squared plus 8n plus 2 is equal to 4k. Then we're going to isolate 2 on the left-hand side. We're letting them know how our algebra is going to work. And we end up with 2 equals 4k minus 4m squared minus 8n squared minus 8n. We're going to factor out the 4, which tells us that 2 is equal to 4 times the quantity k minus m squared minus 2n squared minus 2n. Then we're going to divide both sides of that equation by 4 to get 1/2 equals k minus m squared minus 2n squared minus 2n. And now we're going to do the whole one side's an integer, one side's not an integer. But to prove the right-hand side is an integer, we're going to have to use closure. So since the integers are closed under subtraction and multiplication, and again what that means is that if you subtract and multiply integers together, that results in another integer. It follows that k minus m squared minus 2m squared minus 2n is an integer. However, 1/2 is not an integer, and since 1/2 is equal to k minus m squared minus 2n squared minus 2n, and we cannot have an integer equal to a non-integer, this is a contradiction. So we've made it very clear that we've proven something that is obviously false. And now since we have a contradiction, our proof is complete. All right, so now having seen a little bit of proof by contradiction, I want you to start working on some proofs by contradiction of your own. And those are on the PDF file included with this video.